Hello everybody, and welcome to the last session of this workshop. And my name is Samira Tavakkoli from the University of Duisburg-Essen, and I would like to invite you to pay attention to the first paper of this session. That is about the application of our infrastructure clustering for cloud service placement to enhance user QoE. And this is presented by Dimitri, that Dimitri Chemodanov received his master's degree from the Department of Computer Science at Samara State Aerospace University of Russia in 2014, and he's currently a PhD student in the Department of Computer Science at the University of Missouri, Columbia. And his current research interests include distributed and cloud computing, network and service management, and peer-to-peer networks.
Hello everyone. Guten Tag. I hope you enjoy your lunch. My name is Dimitri Chemodanov. I'm from the University of Missouri, Columbia, and today I'm going to present Dr. Garden's and my research of ApplicationAware infrastructure clustering for cloud service placement to enhance user quality of experience. In my speech today, I will cover basically the first new business models and new business roles for application service providers and the related optimization problem. And then I switch to the case how application-aware clustering can help application service providers. After that, we go quickly through our extension of the non-possibilistic CME algorithm for clustering. To cluster is aware of multiple distances transporting to multiple service level objectives. We also consider how it works on the SkyTap example, one of the application service providers. And then I will say a few words about the model assumptions we have. We then will switch to the performance relation section where we'll basically discuss the main results obtained from both numerical simulations and as well as experiment, and the main findings we have. And we conclude today's presentation just in a few words again about main findings and the future work. So, network virtualization today allows for cloud service providers not only provide their services but also lease the hardware resources for the third parties, making from them infrastructure providers. In this scenario, the interesting role have application service providers who rent these resources leased by infrastructure providers in order to deliver services to the end users or customers. And the main problem they have, of course, is how to deliver the satisfactory user quality of experience by renting less resources, meaning spending less money on the hardware part needed for that. And let's consider the first application service provider example. This is the SkyTap company, the small company who provide the virtual learning environments assumed to work in real time for collaboration between the students and the instructors, so it should be fast and it should work at large scale, means over the world. And of course, such type of service is sensitive to the network quality. And to deal with that, the application service provider claims that he owns a lot of hardware resources from many data centers across the world to ensure that the real time of the services holds, as well as the guaranteed quality of experience. So this is just one example of a situation where really the delivering satisfactory quality of user experience can be complicated by inefficient network design. So what the approach can do with it now? The first one and the main one, of course, application-aware networking. So application-aware networking is the tool when you basically kind of tune your network for particular application demands. For example, you can prioritize the user traffic, like let's consider, let's say, T-Mobile case, right? You have your user data going, you have, for example, the voice data is the most sensitive to the latency, and of course, it will have the highest priority. So what do you need in order to apply this application-aware networking? Basically, you have to have control of both. On the application on the one hand, and on the infrastructure or the network on the other hand. So who can really use such approaches today? The big companies. For example, Google. They have the inter-data center software-defined network called V4, and they also know the traffic which goes through this network. They can prioritize it in a smart way, an efficient way to, on the one hand, utilize resources on the maximum, on the other hand, to improve the quality of the data and, as I said, tune the network for the particular applications. Another approach is the cloud service placement, and currently is used only by the cloud service providers. However, it can be used also by the application service providers. So it's just a matter of API. For example, in Amazon, you can choose the at least availability zone where you want to run your service instance. So the problem with, again, cloud service placement is that just currently only cloud service providers use it for, maximizing their own revenue, to accept more customers, to provide more services, and utilize the resources on 100% level. So to address optimization problem related to application service provider business model, we really need some kind of hybrid between those two. And this kind of a hybrid can be application-aware infrastructure clustering. So how can we cluster the network is aware of our application demands is really just expressing, for example, these demands as a bunch of service level objectives based on service level agreement, right? And then we can decide how many service instances we need and cluster the network in order to understand where to place our services first, and then what part of users these service instances will cover. Again, existing approaches, clustering approaches, usually works with just a single metric, single similarity metric. For example, it can be a single distance metric. Whereas in our case, we have multiple distances corresponding to multiple service level objectives. So to this end, going smoothly to the next section, we extended the known possibilistic CME algorithm in order to cluster network with aware of multiple service level objectives. So how do we do this? The first step, again, we use the external distance function for particular service level objective constraint. And then, based on this distance, we can judge on the possibility of having a path from a particular vertex or node in the network, having the path to the cluster center, and which will satisfy the service level objective. So similarly, you can see, if you look closer at this function, that if our distance is infinite, meaning there is no path, that possibility will be 0. If it's 0, otherwise the possibility will be 1. So, meaning you definitely will guarantee this service level objective constraint. However, to estimate the overall possibility of having a path which satisfies all service level objectives, we use the product rule. Basically, just multiply all these particular possibilities corresponding to a particular service level objective. And finally, we update our cluster center by picking the vertex or node with the minimum distortion within the cluster, and such distortion can be computed as a sum of distances divided by the respective service level objective constraints. And then we can switch to the next iteration and again check if we need one more iteration or not. So let's consider how it works. Assume we have a simple network consisting from 5 availability zones, all inter-availability zone link, which assume to be usually inter-data center link or inter-data center link, but between two geographically close located data centers. And these links have low delay and low loss rate. And we also have inter-availability zone links which already have higher delay, typically corresponding to geographically remote data centers, right? And they need high loss rate. So our goal is to place 2 virtual desktops on top of this infrastructure, such that the one-way delay will be less or equal to 50 milliseconds, and the loss rate will be less or equal than 0.05%. So why 50 milliseconds? To have the seamless responsiveness of the virtual desktop, and low loss rate, to have better, for example, image quality. We also, for the purpose of experiment, have the particular links between availability zone 1, for example, and availability zone 3 to have a high delay, and links between availability zone 2 and availability zone 5 to availability zone 3 to have high loss. So with that example, there is no way how to connect, for example, from availability zone 1 or availability zone 2 to availability zone 3 without any service level objective violation if the server locates in availability zone 3. So the first method we use for clustering is the K-means, also known clustering algorithm, where we use the topological proximity model. So basically, we are trying to minimize the number of hops between each node in the cluster and the cluster center. And it makes sense because many service level objectives are either additive or multiplicative, meaning that the more hops you have, the higher chance that your path will violate one of the constraints. So as a result, we can see that in the first cluster, doing so, the K-means places 2 cluster centers within availability zone 3, as these nodes have the highest average node degree. And in this case, cluster 1 doesn't contain any paths which satisfies fully service level objective. In the cluster 2 situation, will be better. We have only half of the paths which violate the constraint. So now, if we will switch to the possibilistic CME, now we take into account not only hops, but also the distance in terms of loss and delay. We place the cluster centers in the different availability zone and cover the network a bit differently, but it allows us to have both clusters with paths which guarantees service level objective satisfaction. So, the few words about assumptions here. The first one, our model really assumes that local resources suffice. And what we mean by local resources assume that the user connects to the availability zone or infrastructure edge. And of course, if user have low bandwidth or high loss rate, there is no way how our model, which already violates the service level objective required for the using of this type of the particular type of service, there is no way to have a path which will guarantee holding of these service level objectives. And the second one assumption is that our theme is assumed to be mainly offline. So we just deciding where to place our instances and what part of network these instances will cover. So, however, there can be a situation when 2 users, while logging into the remote server, can share the path, and as a result, there can be congestion, which in turn will degrade the network quality on these paths, and which will result in service level objective violation. So, to deal with that kind of online problems, we assume that providers or application service providers can use tools such as load balancing or traffic steering techniques. So our first goal was to understand in which situation it will be better to use clustering based on multiple distances in contrast to other existing clustering approaches for quality risk placement. To this end, we use bright generator to generate topologies, internet realistic topologies followed both Waxman and Bravas output models, where we have 100 nodes and 200 edges. So approximately we have average node degree equal to 4, which again in line with current internet topologies. And we use the following clustering models, where we first just blindly place our service instances and then use geographical proximity to connect to one of the instances, meaning that we pick the service instance which is the closest to the user in terms of geographical distance. For example, it's a familiar situation when you log into some site and it asks you for your geolocation. So another algorithm which we already used an example is again k-means using topological order, which tries to minimize number of hops to the cluster center. And the last one is multiple distance clustering or multiple service level objective clustering based on our PCM extension. And of course, each link has uniformly distributed bandwidth, delay, and some arbitrary cost metric. So our numerical simulation showed the main finding that our PCM scheme, actually you can see that if the number of clusters is too low, for example, if ISP budget is too restricted, right? Or if ISP budget is not restricted, so it can afford itself to place as many instances as you want. So in that case, there is really no benefit of PCM over other solutions. However, if we are somewhere in the middle, right, we can see that PCM outperforms other clustering solutions. I should note that in this scheme, all clustering algorithms does not really find the path from the node to the cluster center. They just kind of facilitate its finding. So basically they decide where will be the cluster center, and then the application service provider or infrastructure provider may use their own routing schemes to forward the traffic between those two nodes. So, and then our next goal was to really estimate the impact of the SLO validation on the QoS and the user quality of experience. So to this end, we recreated our SkyTab example in the Genie-Tab where we separated all availability zones based on some, with geographical distance, for example, we use different sites, like in California, Kentucky, Missouri, and they adjust all link weights using NetApp emulator and bridge all paths using bridge utils, standard Linux tools. So to evaluate quality of service, we use TCP-based SCP command to transfer 100 megabyte file between the server and the user, and to collect quality, to collect data for quality of experience assessment, we use real-time video streaming using VLC player over UDP protocol. And finally, we also created human subjects in order to collect the mean opinion score of these QoE data. So our first finding shows that in the cluster 1, where service level objective validated heavily by all the paths, we can see significant degradation in their throughput as well as in the round trip time, which relates to the delay, whereas our algorithm still allows to fully utilize this 15 Mbps bandwidth channel and have traffic lesser than 100 milliseconds round trip time, meaning then less than 50 nanoseconds one-way delay. In the cluster 2, the situation is a bit better because only half of the paths were validated service object constraints and not that heavily. So there is no violation in round trip time, and the throughput also is a bit better than, is much better than in cluster 1. So the overall we can see that almost 90% of the traffic have throughput of 3 Mbps in both clusters due to significant SLO violation in cluster 1 and small SLO violation in cluster 2. The RTT is a bit better, and our overall QoE of the video streaming also showed that in the cluster 1 we have significant degradation. In the cluster 2 there is almost no difference. Overall one is that our solution shows better quality of user experience over the KEs when we are not violated the service level objective constraint. So based on that results, what we can conclude that first of all, yes, it makes sense to use application-aware clustering. And it will help application service providers to grant less resources from infrastructure providers. The second one, yes, the proposed scheme doesn't tie to a particular routing solution and just facilitates finding of the multi-constraint paths. Finally, we show using both numerical simulation and the experiment results that being in line with SLO constraints helps to provide better quality of service as well as better quality of experience for a particular services. So what we do next? Of course, first of all, we need to really understand how to better combine the proposed PCM approach with the other traffic steering techniques or other load balancing techniques, kind of to be proposed hybrid solution for offline-online traffic management, as well as conduct more experiments to really understand to what extent and what type of services are needed, what type of routing algorithms combined with our possibilistic singing clustering scheme. So that's basically all. Thank you for your attention. Danke schön.
So we have time for maybe one question now. And still any question? So
It's just that you used drive to the topology generation.
Yes.
And I saw some papers discussing that currently, or was it 2009, that the topology generation with drives is not so up to date anymore. So
Yes, I also read that. So
it's just suggestions. It was an internet topology,
so basically, as I know, there's currently no really up-to-date topology generators at all.
There's a topology suite covering around 300 internet topologies, like internet 2 topology, Geon, and 300 topologies of different countries. It might be something interesting just to integrate in the research.
Okay, got it. Thank you.
If you want to read online, which might be very important method to what do you think about the complexity, and do you have to go to the suboptimal solution, or what do you think?
Yes, you definitely need to go to supplementary solutions because the clustering itself doesn't guarantee you that you even will have that pass with guaranteed service level objective, right? So the clustering only facilitates solutions of finding such paths. So to answer shortly on your question, yes, you need definitely couples with some solutions. For example, you can couple at least with load balancing, right? And you have, based on, for example, possibilistic seaming, after possibilistic seaming clustering, you have a kind of hierarchy of cluster centers, right? So the cluster 1, for example, the cluster center 1 has the highest possibility for a particular site. the cluster 2 a bit lower possibility, so we can use it within load balancing to, dynamically change the cluster centers. The first thing. Another thing, the traffic steering itself can be used, but again, for the traffic steering, you mainly need to control the infrastructure. So in this case, application service providers can be limited to do so. But yes, if you control also infrastructure, you can integrate it within traffic steering techniques for dynamic path provisioning, and it will work better.
Okay. Thank you very much, Dimitri, and I invite you, Thomas.